Ladies and gentlemen, I am John Pace, a member of the R.M. Santilli Foundation and the chairman of the World Lecture Series on Hadronic Mathematics, Mechanics, and Chemistry. It is a pleasure and honor for me to present Lecture 1C by Professor Ruggero Maria Santilli on yet another fundamental aspect of contemporary science, the identification of the limitations of quantum chemistry in view of the complexities of nature. As it was the case for the limitations of special relativity and quantum mechanics in the preceding lectures 1A and 1B, difficulty of this lecture stems from the widespread belief that quantum chemistry is exactly valid for all possible chemical structures and processes existing in nature. Professor Santilli recalls that identical electrons are predicted to repel each other rather than attract each other, according to quantum mechanics, and they cannot possibly form a molecular bond. Consequently, Professor Santilli identifies the limitations of the quantum chemical notion of molecular or valence bond. He shows the axiomatic insufficiencies of modified theories using screened Coulomb potentials. And finally, he shows the impossibility for quantum chemistry to represent chemical reactions due to the reversibility of the former discipline contrasted to the irreversibility of the latter processes. As it was the case for the preceding lectures, a technical understanding of this lecture requires a knowledge of the covering Lie isotopic and Lie admissible mathematics and the related branches of hadronic chemistry presented in the subsequent lectures of levels 2, 3, and 4. Serious opinions on the limitations of quantum chemistry should be reached only after acquiring a technical knowledge of the lectures of level 5 on experimental verifications of hadronic mechanics and chemistry and their industrial applications to new clean fuels and energies. Ladies and gentlemen, it is my distinct pleasure and honor to introduce Professor Santilli for the delivery of such an important lecture for the advancement of fundamental scientific knowledge.
Ladies and gentlemen, let me begin this third introductory lecture also with an obvious statement, namely that the achievement reached by quantum chemistry throughout the 20th century are simply astonishing of an obvious historical proportion. And they've been so diversified to virtually enter in our everyday life. Everything that we touch nowadays is a result of a magnificent discovery by the chemists of the 20th century. After having said so, it is my duty and my conviction that I have to bring to the attention of my colleagues that we are far from achieving final chemical knowledge. Therefore, to push forward, to identify the next step in the scientific evolution of our notion in chemistry, we have to identify the limitations of the basic theory used in the 20th century chemistry, which is quantum chemistry. Now, the moment I mention the limitations of quantum chemistry, a number of fellow chemists they feel offended, and such as the hint being that they feel like their discovery are kind of demeaned. No, my intent is the opposite. My intent is to instead to indicate that that fantastic, outstanding discoveries were made by chemists throughout the 20th century, despite the limitations of the basic theory, which is quantum chemistry. Being an applied mathematician and a particle physicist by inspiration, I can also tell that quantum mechanics has been immensely more helpful to particle physicists than quantum chemistry. Quantum chemistry has been helpful to chemists. So rather than offending any fellow chemist, no, I want to emphasize the power of their intuition of achieving such monumental discoveries without a quantitative underlying process. Now, after having said so, I have a strong statement to make. It is my personal opinion I do not expect fellow scientists to agree. Allow me to express it for whatever its value. It is, after studying the issue for some 50 years, it is my deep and documented belief that quantum chemistry is nowhere exactly valid in the chemical world. Let me repeat this strong statement. While, as I indicated, special relativity is exactly valid under certain conditions, those were stated by Einstein, not Einstein followers. Similarly, the case quantum mechanics is exactly valid on the conditions stated by Dirac, Heisenberg, Schrödinger, the founders, not the followers, etc. So there are conditions of exact validity. It is my opinion that there exist no conditions in the chemical world for which quantum chemistry is exactly valid. This is the main objective of this lecture, so give me a chance to illustrate my point, hoping that, that this will initiate a scientific debate, which means with publications in referee journals. Everything that I have to say has been published in referee journals, and I encourage opposing views. Also, everything I have to say is available in free PDF download in the World Lecture Series in the section for the Lecture 1C. Very well, I have organized this lecture into 5 different parts. Parts 1, I would like to identify the limitation of quantum chemistry for the molecular bonds, for the valence bond. Part 2, I would like to identify the limitation of quantum chemistry for the representation of molecular binding energies. Then I would like to identify in the part 3 the limitation of quantum chemistry for chemical reactions, which is the central topic of this entire series of lectures. Then I would like to identify the limitation of quantum chemistry for living organisms. And finally, I would like to close this lecture with a few remarks regarding the limitations, which are substantial, of available analytic equipment. Very well, let's get started with part 1. Dear ladies and gentlemen, again I have to start with a strong statement. I beg you for leniency. I am not expecting you agree, but at least consider my 50 years of meditation and thinking on the subject. The strong statement is that I have never accepted the 20th century notion of valence, beginning from my studies in the PhD courses at University of Torino in the mid-60s. And the reason is that I consider the 20th century notion of a valence a pure nomenclature without a quantitative scientific background. Let me make the statement. I consider the notion of a valence or molecular bond, according to quantum chemistry, pure nomenclature without quantitative scientific background. Why so? Well, because for me, for a notion of a valence to be really quantitative, first of all, I need the equation that represents the attractive force between valence electron pairs or valence electrons orbiter. I need the equation that identifies the force. Until the equation is identified, my entire conception of a scientific process is like missing the foundation. After identifying the equation, this quantitative treatment has to prove that that force is attractive. Now keep in mind we're talking about identical electrons. Identical electrons repel each other according to quantum mechanics. So you start to see the difficulties for passing from a nomenclature to a quantitative scientific process. And finally, the 1 and 2 are not enough. After proving the existence of an attractive forces with equation and proving that it is attractive, that quantitative process has to be in agreement with the experiments. The solutions, or at least a preliminary solution of those quantitative issues, has been a primary motivation for building new mathematics and then building a new physics, hadronic mechanics, and then passing only at the end of this long process, passing to build a covering of quantum chemistry known as hadronic chemistry. Notice that quantum chemistry was built only after first the mathematics of quantum mechanics, Hilbert space, etc. And then quantum mechanics had to be built. And then quantum chemistry could be conceived. Well, we had to repeat the entire process. That's why it took, ladies and gentlemen, it took decades. However, this process has been completed now and is available, published in referee journal, books all over, in all developed countries, available for all young minds with a minimum of scientific curiosity. To begin, let me bring your attention on the mystery of the valence bond. For this reason, I have selected in the introductory part of this lecture, as you may have seen, a view of the temples in the Far East that gives precisely an impression of mystery to us from the Western world. I also selected an appropriate music by Albinoni to illustrate and again to convey this sense of mystery. Why mystery? Well, this is an hydrogen atom. The hydrogen atom is a perfect sphere, as we know. Perfect sphere because of rotation due to temperature, also as well known. The point is that all total electromagnetic characteristics of these atoms are zero. The total charge is zero, total electromagnetic and magnetic, everything is zero. So the big mystery, how nature makes the miracle of bonding together two hydrogen atoms very tightly, because the binding energy of a hydrogen molecule is 110,000 kilocalories per mole. It's very substantial. So how this miracle is done? Well, this is a very deep question, which is at the very foundation of quantum mechanics, has been unable to solve it in any quantitative way, in my knowledge. So therefore, hadronic mechanics address this issue and is a central topic of research for us. Basically, in view of this mystery, the notion of valence essentially correlated the electrons in a rather weak way. In other words, one of the first insufficiency of the notion of valence of the 20th century, in my personal view, is that the correlation between the valence electrons is not sufficiently strong to justify and achieve the representation of the hydrogen molecule. But it is kind of a loose distribution of orbitals around the pair of the two hydrogen atoms. Due to this generic correlation rather than a bond, a strong bond, then there are a number of consequences which have to be identified. They are not spoken in no PhD course in quantum chemistry that I know all over the world. But this is not the case here. No, we are interested in knowledge, not in politics. And so therefore, if there is an insufficiency, I intend to bring it to the attention of receptive colleagues with a curious mind. Okay, let's start to see the consequences of the valence of the 20th century notion of valence bond. One of my graduate students proved that under such a loose notion of correlation, weakly correlated orbitals, then the hydrogen molecule can have an arbitrary number of constituents. I repeat, one of my graduate students proved that under the 20th century, not the current, 20th century notion of a valence, there is no need to have H2. We can have H3, H4, H5, H6, H7, etc. Of course, with decreasing probabilities. At this moment, and it's very easy to predict, if the orbitals are very weakly correlated, sure, they can have, then the same orbital, they can take 3 and then 4, etc., etc. Now, at this moment, careful about derailing due to politics, because the chemists immediately bring to your attention that the H3 has been measured. Yes, indeed, it has been measured in GCMS, in gas chromatography. Is routinely detected the 3 atomic mass unit structure. So you see, it exists, so it's true, so the notion of valence is correct. This is politics, ladies and gentlemen, because it's epistemological, conceptual, without calculations, without a scientific process underlying it. And in fact, if indeed there exists a valence bond among 3 hydrogen atoms. It's very easy to prove, once you do the calculations rather than the politics, it's very easy to prove that, that the binding energy of 2 hydrogen atoms is a small fraction of what it is in nature. And that is very easy to separate one hydrogen atom with a fraction of the separation energy that is actually needed in nature. So no, this is in reality when the H3 means that there is it gives you the first hint that there are forces, bonding forces in nature beyond the valence. That is scientific, at least you have to suspect it when they detect H3 in nature. But this is only one of the inconsistencies. There are many, many others. For instance, another graduate student of mine has proved that since we are talking about a loose correlation, remember, we are talking about a loose correlation among the valence bond, loose correlation, rather than strong attractive force among the valence electron. That's a dramatically different situation. Then it's very easy to prove that all molecules are paramagnetic. I repeat, it's very easy to prove that under the 20th century notion of a valence, all molecules are paramagnetic. Why? It is obvious. Sure, I've done the calculation, otherwise I will not reporting here. I have inspected the calculation. but you can do it on your own. If the orbitals are so loosely correlated, ladies and gentlemen, then all the orbitals can be oriented under an external, sufficiently strong magnetic fields, and therefore all molecules are paramagnetic, resulting in something in dramatic disagreement with nature. Dramatic. For instance, the hydrogen molecule is diamagnetic, cannot be magnetized. So just by looking at this any proof that this is possible under the valence disproves, or at least indicates that there are the structural insufficiency in the very conception of the notion of valence of the 20th century. Let's go a little bit deeper to examine what type of the conception, the evolution of the notion of valence. Well, it started with this type of loose representation of molecule. This is the methane, CH4. As you can see, there are kind of links in between. This is a preliminary conception. Of course, this is good for a crystal, but not for a molecule. But nevertheless, it was as a nomenclature, as a mnemonic representation. Certainly, illustrates a certain value. Then, of course, the sufficiency of this was known to all chemists. So, so they passed to the notion of mutual penetration of the orbitals, which is clearly an improvement over original conception such as the preceding one. But again, ladies and gentlemen, I do not see the equation producing an attractive force when the orbitals penetrates one inside the other. I have to repeat this point. Without the production of an equation and the quantitative process that produces a real attractive force between different atoms under condition of mutual penetration of the orbitals, ladies and gentlemen, we do not have a quantitative scientific representation of molecular structure. Period. We can discuss what is the next step. Yes, this is debatable, but the insufficiency of this type of conceptual, epistemological notion of molecule cannot be denied without passing the boundary of science, crossing those boundaries and passing into politics. What is the root of the problem? The root of the problem is very, very deep, ladies and gentlemen. It is due to the fact that identical electrons repel each other according to quantum mechanics. Identical electrons repel each other according to quantum mechanics. I have to state and restate because it is ignored, even in the most advanced PhD courses in quantum mechanics and quantum chemistry. So this is against the very existence of a molecule, is against the axiom of quantum mechanics and chemistry. So this is what it goes behind. Not so much the orbitals. The electrons have to attract each other. Now you start to address the transition from a loose correlation among electron orbitals, this is epistemological notion, to a quantitative problem. Strong correlation among valence electron pairs in singlet coupling as requested by Pauli principle. So this is the problem, this is the issue, this is the topic, this is the conditions that are structurally beyond quantum mechanics and quantum chemistry. Why? Well, because they are known nowadays, but unspoken because of the unfortunate politics in the field. Namely, what we have now, remember, electrons can be considered as point-like particles, that's what everybody says. And so, which is true, as far as the charge is considered, electrons indeed have a point-like charge, which is an excellent statement, which is true to an excellent approximation as proved by electrodynamics in any case. But electrons do not have point-like wave packets. Point-like wave packets. No, this is politics, ladies and gentlemen. Electrons have an extended wave packet that, of course, with a density decreasing inversely proportional to the distance, which means in theory one electron fills up the entire universe. And that's the majestic complexity of the universe, that is a single integrated object no matter what the distance is. But let's go back to the electron pairs. Okay, what is the interaction that you see? Of course you see Coulomb interaction, this is obvious. That's what quantum chemistry. But it's not enough, you have additional interaction. What interaction? The non interactions of the lectures 1 and 2, 1a and 1b, namely the interactions do mutual penetration and wave overlappings of the valence electrons. What are those interactions? First of all, these interactions are known to be non-linear. Careful, non-linear in the wave functions, powers of the wave function. Already this eliminates quantum mechanics because you violate the superposition principle. You cannot study complex structure in the violation of the superposition principle. But that's only the beginning. Then this is, you look at this, the look at this implies that the topology underlying quantum mechanics and quantum chemistry is inapplicable to the valence, because you have a finite region of overlapping that you cannot reduce to a finite number of isolated points. Remember from lectures 1a and 1b, the topology underlying special relativity, the topology underlying quantum mechanics, and therefore the topology underlying quantum chemistry is local differential, which means can only describe consistently and beautifully, when applicable, a finite number of isolated points. Here, no, forget about it. You have extended object in condition of mutual penetration. So you need a new topology. It has been constructed, ladies and gentlemen. This is now part of history for us. It's an integral differential topology. And finally, those interactions are of contact type. What does it mean they are contact? It means they have zero range. Imagine, so there is don't even think about a potential, because if you grant a potential to contact interaction, it's like describing the spaceship during re-entry in atmosphere that is on a decaying orbit. You describe it with a potential. This will be total non-scientific nonsense. No, those are interactions in which the notion of potential energy that does not exist. Therefore, those interactions cannot be represented with a Hamiltonian. Therefore, ladies and gentlemen, those interactions are structurally beyond any dream of representation via quantum mechanics and quantum chemistry. Because both theories are strictly Hamiltonian. This means that time evolution is strictly unitary, because the Hamiltonian is Hermitian, being unobservable. So the the ultimate essence of molecular bond is conceptually, mathematically, epistemological, and as we will see experimentally in level 4, is beyond any dream of representation with quantum chemistry. And this is the first of a long series of reasons that illustrates my strong point at the beginning. Namely, it is my deep conviction after 50 years of study of the topic that there exists no chemical condition in the universe for which quantum chemistry is exactly valid. As an approximation, oh yes, then depends on the approximation, there's a completely different issue. Now, those are the interactions that are the central topic of study of mathematics, of the covariant mathematics that we have developed, Lie isotopic, Lie admissible, hyperstructural, etc. These are the interactions that are the foundation of the covering hadronic mechanics And those are the interaction at the foundation of hadronic, the covering hadronic chemistry that has been crucial to achieve the new clean energy and fuels which are presented now already developed in the industrial developed at the industrial level in numerous countries, including China, India, Europe, etc. Okay, now, but what is the fundamental point that has been the guiding principle throughout all those studies, which I have to present in this introductory lecture? In the subsequent lecture of level 2 and 3 and 4, those will be technical. I will not review these things that are considered nowadays elementary. So, what is the main point? The main point that those interactions are non-Hamiltonian. Namely, you can represent in any way you want except using the Hamiltonian. What is the consequence of this central feature? The consequence is that the time evolution of the applicable theory can be asked necessarily to be non-unitary, because if it is unitary, then you are within the class of equivalence, a unitary equivalence of quantum chemistry. Then you go back to a Hamiltonian, you change the Hamiltonian, you add some crazy terms that derails the scientific issue, and you get publication, grants. Sure, this is possible, but I'm not interested in that type of process. No, interested in the foundations. So this is non-Hamiltonian. This means time evolution has necessarily to be non-unitary in time. The time evolution has to violate the condition of unitary. This is the reason why in 1978 I proposed, when I was at Harvard University, on the support by the Department of Energy, I proposed the construction of the covering of quantum mechanics under the name of hadronic mechanics, with the central feature of being a non-unitary covering. And of course, one of the central point that I addressed was the non-unitary covering of the Schrödinger equation. And even in the original paper of 1978, I proved that with a non-unitary covering of Schrödinger equation, I can do things that with quantum mechanics you cannot, such as represents the pi-0 meson as a bound state of an electron and a positron, a compressed positronium, if you want. This is impossible with quantum mechanics because the the resulting energy of the bound state, which is the pi-0, is about 135 times bigger than the sum of the rest energy of the constituents. The conventional Schrödinger equation is totally inconsistent, but not under a non-unitary unitary map. Under the unitary non-unitary covering of Schrödinger equation allowed the representation of the all characteristics of the pi-0, beginning with the rest energy, as a bound state of an electron and a positron. And now this principle has been applied at all levels, including, it's way advanced now in the numerous level of chemistry, as we will see in level 4. Very well, let's pass now to the second part, namely identify some of the limitations of quantum chemistry for the numerical representation of molecular binding energies. Again, I have to bring to your attention the mystery of nature, and hoping that has been inspired, this mystery has been inspired by this beautiful temples for the Far East that you have seen in the introductory part. But what I'm talking about, what type of mystery I'm talking about? Well, the mystery is the following. That you see, suppose this is an hydrogen atom. I stated insistently in lecture 1b that quantum mechanics is absolutely exactly valid for the representation of the entire phenomenology of the hydrogen atom to such an extent that it is astonishing. Because from first axiomatic principle, without manipulations with unknown parameters and functions, the Schrödinger, Heisenberg, Pauli, and the other founders managed to represent the totality of the spectral line to an accuracy which is astonishing. Fine. Now we have two hydrogen atoms put together in the hydrogen molecule. Question: are quantum mechanics and quantum chemistry correct, exactly valid for two hydrogen atoms bound together into a hydrogen molecule? Ladies and gentlemen, the answer is absolutely not. Indeed, quantum mechanics and quantum chemistry becomes only approximately valid. So you have a transition from exact validity for one hydrogen atom to only an approximate validity for the two hydrogen atoms bound together. Very well. But now let's see what type of approximation we have. Now, it is generally believed that the approximation is very good. As you can see in the transparency, when we use quantum chemistry from first axiomatic principle without manipulation with arbitrary parameter and arbitrary function fitted from the data, under those conditions we miss 2%. It is generally stated that this 2% is small, so therefore the approximation is good. Ladies and gentlemen, I disagree. There is a political derailing here. 2% of the bind, as you can see in the transparency, 2% of the missing 2% of the binding energy of the simplest possible molecule, which is the hydrogen molecule, corresponds to 950 kilocalories. That is the equivalent thermal energy contained in 1,000 cubic feet of natural gas. I repeat, the error by quantum mechanics and quantum chemistry in the representation of the simplest possible molecule, such as the hydrogen atom, corresponds to the thermal energy of 1,000 cubic feet of natural gas. Ladies and gentlemen, I have no interest in an academic career. I never had and never will. I am interested in knowledge. Above all, I cannot compromise on ethical issues. When there are insufficiencies in science, I always did and I always will. I will indicate them. For receptive scientists who are outside organized interest on existing theories. Well, ladies and gentlemen, the obvious question is how is this possible that that for one hydrogen atom we have such a fantastic exact representation, and when we go to two hydrogen atoms bounded together, this fantastic exact validity is lost in rather substantial amount, not small, substantial amount. We got to go deeper into this and identify the origin. Otherwise we also do politics, not in this series of lectures. No way. Okay, this is the difference. This is the hydrogen atom and this is the hydrogen molecule. What's the difference? Ladies and gentlemen, the difference in the non interactions. That here the distance of the orbiting electron from the proton is proportional to the distance of Earth to the Sun. They are very far away. As a result, the structure of the hydrogen atom does indeed allows an exact validity of the topology, local differential topology, as well as the only potential interaction, therefore Hamiltonian, therefore unitary time evolution, the entire quantum mechanics, the foundations of, just by looking at the structure, you can see the validity of the conception of the originator of quantum mechanics for the original system, not for the talking about the original conception by Pauli, Heisenberg, Schrödinger, not the followers who have applied this, have adulterated this beautiful original conception for personal gain, essentially, because extended the applicability under conditions immensely beyond those of the originators, therefore abusing the name of the originator to get grants, chairs, and so on. Not in this series of lectures, no. Okay, so let's go down to the structures. You see, again, is the non interaction when the electrons, valence electrons, stay coupled in singlet, we exit. So, when we go deeper into a molecular structure, we see interaction among identical valence electrons, of course, in singlet coupling, to verify Pauli principle, that violate virtually all aspect of both quantum mechanics and quantum chemistry. Beginning first of all with the mathematics, the topology, the Hilbert spaces, etc. The Hilbert spaces are linear, those are non-linear interaction, etc. But then all the way to, also from an experimental viewpoint. I shall indicate that one of the central objectives of the covering hadronic chemistry has been precisely the valence bond. I have achieved this valence bond with Professor Schilledy, an academic chemist, and the bond is today called Santilli-Schilledy strong valence bond, namely a bond that is specifically restricted to two valence electrons with a clear identification of the equation producing the force, the verification that the force is attractive despite the Coulomb repulsion, and the verification that indeed such a notion of a strong valence bond represents the binding energy of an hydrogen molecule exactly to essentially to the desired decimal. But in this case, however, H3 is prohibited, as you will see in a moment, and so on. Now, this was the situation was known already by the middle of the past century. I should say 60s or 70s already. This insufficiency of in the representation of binding energy was well identified by quantum chemists. So the question is, what quantum chemists did? Well, in the last part of the 20th century, what they did is they introduced so-called screened Coulomb potential. What is the point here? The point is the following, that the Coulomb potential alone cannot allow an exact representation of molecular binding energy because of this missing amount that we have indicated. Okay, so what they did the screening, namely they multiplied the Coulomb potential by an arbitrary function, FOR, and this arbitrary function was fitted from the experimental data, and in so doing, indeed, an exact representation was achieved. So clearly this is a step forward with respect to the original notion of valence coupling and quantum mechanical representation of molecular structure. Indeed, there has been even a Nobel Prize in chemistry granted on this point alone, fully deserved, my God, because human knowledge is a sequential step of motion forward, is a chain, an integrated chain. However, this is a series of lectures in which I intend to avoid politics to the best I can possibly can. Actually, identify politics when one is there. With the full understanding that the research on screened Coulomb potential are indeed valuable, as you will see in a moment. I will elaborate this in a moment. With that clear understanding, what is very questionable, and in my personal view, political, is claiming that screened Coulomb potential still characterize quantum chemistry. Why so? Well, it's the very principle I cannot accept. There is an arbitrary function here. Arbitrary function is fitted from the data. And we have no idea what this function is, no physical notion or whatever. And once this function is fitted from the data, then quantum chemistry is claimed to be exact. Ladies and gentlemen, I'm sorry, I cannot accept that. I respect the work of others, respect my view, so that I can respect yours. Why I respect the calculations underlying screened Coulomb potential, but I do not respect the dubbing of quantum chemists? For many, many reasons. Here I have three of them. First of all, it is obvious to even a first-year graduate student that screened Coulomb potential cannot have quanta of energy. I repeat, quanta of energy exists for the Coulomb potential in the hydrogen structure. The moment you multiply the Coulomb potential by an arbitrary function, the very idea of a quantum of energy, that the energy is exchanged with according to quanta, makes no sense. You have no longer quantized orbit, everything that we know for quantum mechanics is gone, ladies and gentlemen. Show me the equation otherwise. You will waste your time because this has been proved. FST graduate students can prove that there is no quantized exchange for screened Coulomb. So the dubbing of the resulting theory as a quantum chemistry, I'm sorry, it's political, but has no scientific foundations. So first year graduate students know that Galilei and Poincaré symmetry are generally violated, are broken, as sometimes is said, for screened Coulomb potentials. But then here's the issue. Under the violation of those fundamental space-time symmetry, any claim that the resulting theory is still quantum chemistry, ladies and gentlemen, is political, has no scientific foundation, in my view, and best knowledge. Finally, but this is on, there are many other reasons. I don't want to, this I'm presenting only the very, very top of the most visible aspect. There are very deep issue. But another one I have to present here is that the map from the Coulomb to the screened Coulomb is non-unitary. Remember, Coulomb potential is the fundamental invariant of quantum mechanics and chemistry. So the only way to go from being an invariant to the time evolution of both Galilean and Poincaré symmetry, being an invariant, the only way to go from Coulomb to the screened Coulomb is via non-unitary transformation. What is the outcome? Ladies and gentlemen, the outcome is that screened Coulomb potentials are a realization of hadronic chemistry. I repeat, what are still called quantum chemistry, in reality, since as a necessary non-unitary map, you need necessarily non-unitary map to derive it, is a realization of hadronic chemistry, because hadronic chemistry, by conception, is as a non-unitary time evolution law. As a matter of fact, hadronic chemistry allows the representation of an infinite number, in principle, of infinite variety of screened Coulomb potentials. And so what those are used in quantum chemistry are only very elementary. The covering hadronic chemistry can identify, first of all, the origin of the screening is that the non-interaction causes the screening. And secondly, can represent them in an axiomatic way without throwing arbitrary functions, and then without throwing parameters. And so this has already been done by Don Schillerdy and myself in a variety of papers published in referee journal, International Journal of Hydrogen Energy, and they're available in free PDF download in the World Lecture series. There is one point very, very deep here. That is why while as far as the elaboration is concerned, I consider screened Coulomb potential very valuable. However, the politics, after you cut the politics out, in my view, this of course is not stated in the literature of quantum chemistry. Quantum chemistry is the loss of the notion of quantum in the screened Coulomb potential is very, very deep, ladies and gentlemen. It goes at the very root of why quantum mechanics and chemistry are not exact and cannot be exact for molecular binding energy. What is the point? The point is elementary, ladies and gentlemen. Let me go back here. Here you see, these are quantized level. This is the ground state, the Bohr orbit, but then you have an excited state and you have additional states, and therefore the exchange of energy are necessarily quantized, as it is well known, and I have emphasized in the lecture 1b to prevent manipulation of those lectures. The point I'm referring is here, question, are there excited states of the hydrogen molecule? The answer is no. I repeat the statement. The hydrogen molecule is one and only one, and admits no excited states. So this means that the very notion of quantum is absent, is eliminated by nature in molecular bonds. This is the deep meaning of the fact that the screened Coulomb potential cannot have any quanta, and it's very, very deep. It's connected ultimately to a point we have already raised in preceding lecture 1b on quantum mechanics. Namely, some of you may remember, if you had the chance to look at that lecture, an electron, when member of a hydrogen atom, necessarily can absorb or emit energy according to quanta. This is established. I have to repeat it again to avoid derailing and intentional misreading of my lecture. However, the issue is when the same electron is in the core of a star, are the energy process still quantized? Ladies and gentlemen, then you enter it. If you say yes, then it's a pure theology with no experimental verification whatsoever. The electron is immersed in an ultra hyperdense medium. How can it possibly jump to get energy? This is, ladies and gentlemen, no, we have to assume the most plausible hypothesis beyond the politics of quantum mechanics and chemistry. The most plausible hypothesis is that electron in the core of a star has energy exchange which are integral differential. And of course, when the electron is then goes back in empty space, you recover the quantum. It's exactly the same situation here, ladies and gentlemen. It already see the beginning of the loss of the notion of quantum here at the molecular level. And I do not know how many colleagues, in both in physics or chemists, are ready to abandon the notion of quantum as a necessary condition to go higher in the scientific mountain and see broader vista. That remains to be seen. Here I just want to sketch the Santilli-Schiller strong valence bond, which you see the moment the two electrons are bonded very deeply with a very strong attractive force of non-Hamiltonian, non-potential nature, then the pair of the two bonded electrons, they describe a kind of O-shaped trajectory around the two hydrogen atoms. What are the consequences? First, an exact representation of the binding energy virtually to the desired decimal, if you want. It's been proved in the papers published in referee journals. But it's not enough. This also removes the inconsistency that I have indicated before. You can see here that this molecule cannot be magnetized, cannot necessarily diamagnetic, because the two magnetic moments are opposite to each other. So therefore, this will never be a paramagnetic molecule, as it is when the electrons are weakly correlated, because the quantum mechanics chemistry do not know how to handle the attraction among two identical electrons that are supposed to repel each other. And also also notice that the third electrons cannot be included here, because the moment this pair goes into third electron, then this is free. And that's the point I made before, that if you accept the H3 as a molecule, then, you have all sorts of inconsistency in the binding energy of H2.